Hey, how's it going? Yeah, let me get my VS Code set up and yeah, let me go ahead and um share my branch. Okay, give me 1 second. Okay, let me go ahead and get started. Share my screen, entire screen, screen one. Okay, yeah, so basically whatever is in scope is essentially within this. Do you guys see my screen by the way? Okay. So basically, everything in SRC would be in scope except for the limit order lens. So the limit order lens contract, this is just pretty much a view only contract just so users can see their positions. We use it in some of the tests, so I kept it within the file, but any bugs in there is considered out of scope. We'd rather have people focus on bugs that are going to affect, like the write only or the write functions within the limit order manager contract. So I'll just give a quick overview. Basically, what this contract does is it has automatic execution of limit orders on Uniswap v4. And so a limit order is essentially a single-sided liquidity position, either in token 0 or in token 1. And for example, let's say it's ETH-USDC. If you wanted to you're always selling the token. So if token 0 is ETH, that means you're selling ETH. If token 0 is false, that means it's USDC and you're selling USDC, or essentially you're buying ETH. And so the way that it works is through two hooks on Uniswap v4. It's the before swap hook and then the after swap hook. So we get the before swap hook before the swap takes place, we store it in transient storage. And then in the after swap hook, we get the tick after the swap, and then we execute the order from a separate contract called the limit order manager. And so we pass through the tick before swap and then the tick after swap. So essentially what this is doing, it's scanning through the tick before swap and tick after swap and seeing which orders we have to execute, and we'll execute all the orders through the after swap hook. So one of the major things that we're looking here is, potential denial of service attacks or even out of gas errors, because the swapper is essentially paying to have the liquidity position burned. And so potentially it could get quite expensive for the swapper. So what we've tried to do with this contract is to really maximize the gas efficiency in terms of, that's why we store it through transient storage with the before swap hook. We're trying to minimize as much gas usage as possible to the actual swapper himself. So let's look at the limit order manager contract. This is really where the main um, the main logic is being stored. Pretty much all the logic is really within the limit order manager contract. And we use enumerable sets for storing the user's positions, which we have as position keys. We whitelist certain pools that the user is can so whitelisted pools are pool IDs. So we don't have permissionless creation of pools like, oh, I want to create limit orders on this pool. It has to be a whitelisted pool. Um, and yeah, so we have all these different mappings of pool ID. If you guys don't know, pool ID is essentially like an encrypted pool key, and a pool key on Uniswap v4 is essentially token 0, token 1, the fee tier, the tick spacing, and the hook contract. Um, and essentially, we also have, yeah, so we have different mappings of the user positions, the nonce of the positions. So the reason why we nonce here is for every single position, like let's say, we're in a single tick position on an ETH USDC pool, uh, it can potentially get executed, and then the price could move back, and somebody could create that position again. But the prior position still needs to be claimed. So that's why every time a position is executed, we increase the nonce for that particular position on that particular pool. We use tick bitmaps to scan through the positions. So as mentioned earlier, we're trying to be as gas efficient as possible. So we're essentially using Uniswap V3 libraries or V4 libraries for tick bitmap to efficiently scan through ticks that have limit orders, and we're storing the limit orders within the ticks themselves. So basically, the main function is create limit order. We specify whether it's token zero or not. Again, this is always a token that you're selling. So if it's ETH USDC, ETH is token zero, we're selling ETH. Or if token zero is false, that means we're selling USDC. But another way to frame that is we're buying USD or we're buying ETH with USDC. So we pass through, is token zero, the target tick, where we want to sell it at, the amount, and the target tick. These are all dependent on. So this library, tick library, get valid tick range. It's gonna show you exactly what ticks are possible because I don't know how familiar you guys are with Uniswap V3 math or tick math, but essentially, if you have a token zero order, it can only be placed to the right of current tick, and if it's a token one order, it can only be placed to the left of current tick. So this library right here, get valid tick range, is doing exactly that. It's the logic for where the ticks can lie. And so you could see that there. So let's go back to the limit order hook, the limit order manager. And yeah, that's essentially it here. We also have an option for creating scale orders. I don't know if you guys are familiar with Hyperliquid at all, but on Hyperliquid they have this option for creating scale orders. And what happens on scale orders is that you can specify the bottom tick, the top tick, the total amount, the total orders you want, and the size skew, and it'll create orders accordingly. Let's see. Well, just to give you guys an example, like really, we tried to mimic Hyperliquid here. So if we were trying to make a trade, um, let's say for they have scale orders on Hyperliquid, and basically, let's say if I want to buy BTC and I want to buy like $100 worth, you could specify a size skew. So basically, a size skew is a ratio between the starting and the ending price. If the skew is two, then the limit order for the end price will be twice the size as this as the starting as the starting price. So if is twice for the end price as it will be for the starting price. So let's say if we just have two orders here, then the second order will be twice the size of the first order. Or essentially the last order is going to be twice the size of the first order. So that's really the math. And if this is less than one, for example, if it's zero point 0.5, then the inverse is true. The first order will be twice the size of the second order. So that logic you'll find here. Um, Validate and prepare scale orders, and then you'll pass through in the tick library. It'll return exactly what the an array of different positions that you're going to have. um and essentially that goes into both of those functions called the internal create order function. Checks against the whitelist, it's pausable. um Validate scale order size or calculate scale order sizes. This is the one where it takes into account the size skew. So in terms of, yeah, calculate order size, this is the math that determines the size skew. As what I told you earlier, if sky skew is 2, then the ending order should be twice the first order, um, and so on. And so, okay, so that's creating order, canceling the orders. Um, we have the ability to cancel in batch. And basically, what a cancel order does is it removes the person's order and it claims it at the same time. So it reduces the order, it retracts their position fees. So retract position fees. So one of the main tenets of this contract is that, or the main benefits of this contract is that you can place limit orders, but the fees that you earn is essentially going to be owed to um, the limit order creator. Um, but the issue is, what if you have multiple people within the same position? How do you allocate the fees to each contributor equally, or in you don't actually want to do it equally. For example, let's say if somebody creates a limit order, it's one tick spacing, so ticks 10 ticks, and let's say part of the order it goes into the tick range and then the price pulls back. So the original contributor within that position has a certain amount of fees, but what if somebody else deposits into that position and then you have another swap that goes partially in there. A portion of the fees belongs to the first position contributor, and then a portion of the fees should get divided evenly between the two afterwards, right? And so that logic takes place in retract position fees. So basically what this does is it handles uh, the the accounting, the fee accounting. So essentially what we're taking is the fee. So if you guys are familiar with the synthetic staking contract at all, it uses that same type of logic where it takes like the rewards uh, per amount, but except we call it fee per liquidity. And so we take the fee per liquidity, the global fee per liquidity, and we update it using essentially this is using it was quite a big function. So it's just using full math where it's taking like the fees that were the last updated from the position and distributing it to the global fees per liquidity. And whenever a user deposits, they adopt the global fees per liquidity, very similar to the logic of the synthetic staking contract, where, if you're a new user, you get, as soon as you deposit, you get the global fees per liquidity or reward per token is what they call it on the synthetics contract. And the reason we have that is so we don't have to iterate through everybody's position and update what their right amount of fees would be. You get essentially the global fees per liquidity upon deposit. And then upon withdrawal, you take the difference between like your own fees per liquidity and the global fees per liquidity, and that's going to be how much tokens that you were owed or how much fees that you were owed. And the logic for that is very, very similar to the synthetic staking contract. So let's basically this function here is what updates everybody's fees. And yeah, and uh, the next main function here is execute order. Let me just see. So execute order, this is what's being called from the hook contract. It requires, message center to be the hook. This is what we saw earlier in limit order hook. And find overlapping positions. This is the main function that scans through all the different functions. And this is really using, so it's taking, the tick before swap, tick after swap. It's taking the direction of the swap. 0 for 1 means it's going right to left. Uh, this being false means it's going from left to right. And it's using the tick bitmap library mainly to find, where the next initialized tick is. Um, and yeah, and essentially execute order, it's another part of this is Pretty much every position, every user position is going to be within each tick is just one position. So, let's say if tick from tick, let's say the tick spacing is 60 and we have 0 to 60 as a tick for a particular limit order. Um, Anyone who contributes to that liquidity position from 0 to 60 is essentially depositing to the same liquidity position. We're not having multiple liquidity providers, multiple positions from tick 0 to 60. Everyone is going to provide in that same liquidity position. That's really getting back to that gas efficiency we're searching for. But let's say we have a 10 tick spacing pool and there's a huge swap that takes place. um, Potentially, let's say it goes over 750 ticks. What we've determined in our testing is that once you get to around like once you're executing like 100 positions, you're running into the gas overhead limit. So we created this executable positions limit. Hardly ever is this ever going to be called because it's pretty efficient where it could execute up to, let's say, 75 positions, no problem. Uh, even 100 positions, no problem. And if it only just goes, and what this means is it's going actually through 75 tick spacings, and that's quite a lot for a big swap. And like hardly ever will you ever see this on a swap that takes place that goes 750 ticks in one swap. So almost never will we ever run into that case. But just in case we do, we created like this executable positions limit. We set it to 75, and basically the leftover positions are going to be handled by a keeper account. And so we have keeper logic here. Uh, so this is going to emit positions left over, and then we have function execute order by keeper. Basically, what this is going to do is we're going to run separate keepers. It's going to execute these positions based off whatever positions are waiting or whatever positions were not executed. And even if they were not executed, like let's say if the position pulls back and then another swap takes place, those will also be subject to execution, even regardless of whether the keeper executes the positions or not. And we don't think this will ever happen, especially for like where it might happen is for like certain maybe LST single tick spacing pools where it goes 750 ticks. But even that is going to be very, very rare. If probably maybe if somebody takes out a flash loan that could potentially take place, but almost always we don't ever expect the keeper to come into action. But just in case, we have this ability there. So yeah, that's essentially it. I think where a lot of we updated the repo with we had a pass audit from Guardian. I think we had quite a few errors in terms of something that in Guardian what we changed majorly was this find overlapping positions. So before what we did was in the Guardian audit, we had this is new code since our last Guardian audit. What we had earlier was that we stored all the orders in order, like, and pretty much we weren't using the tick bitmap approach. We just stored all the positions in order, and essentially that led to potentially a lot of out of gas errors when there was a lot of positions. So that's another thing to keep in mind. Like what happens if there's an attack where a user creates like 12,000 orders, right? You're going to be having to search through like potentially 12,000 orders. And that's why we implemented the tick bitmatch approach, where you're only searching between the tick before swap and the tick after swap. And let's say, uh, and so there's only a limited number of orders that you could potentially scan for. So that's going to drastically reduce that. But this part hasn't been audited at all. So if maybe there's something wrong with this approach, that's maybe something to look into. Um, but yeah, I think that's pretty much it. I think canceling orders was a pretty big like DOS error here too. I think when you're canceling the orders, let's see, function, cancel order. I think it's the internal function. This one, you potentially have to scan through all the orders. There's like a, let's see, execute tick, suitable tick handle, position removal. Yeah, I think when you handle the position removal, you claim the order, you remove position. Well, I think no, this actually became a lot more gas efficient with the tick bitmap approach because the orders are actually stored within the tick. Like before, what we had was that all the orders were stored in order. So when you remove the position, you had to move everything within the array so that the array stays in order. But obviously here now we use a tick bitmap, we just remove its position from the tick. And so this makes it a lot more efficient. Ordering no longer matters because the orders are stored in the tick. So that out of gas error, hopefully we fixed with this potential function here. But yeah, I mean, happy to maybe take a breath and see if anybody has any questions on any parts of the code. But that's at a high level what the code is doing. Users are placing single-sided limit orders and single tick spacings, and then in the after swap hook, the swapper is executing the orders with his swap. And if it goes through tick spacing, if it hits the right ticks and find overlapping positions, it'll find those ticks and it'll execute those ticks in the execute order function in the limit order manager. And this is really the main contract that stores all the logic. The position management, this one just adds positions to the ticks, removes positions to ticks, calculates position fees. We pretty much decode each position, and we take like the bytes 32 hash of that position as the position key. The position key consists of um, pretty much what does it consist of? Is like the pool ID, bottom tick, top tick is token zero, and all that stuff is hashed together to create a position key. And those position keys are used within the mappings here. It goes from pool ID to position key to enumerable set or what else and what have you. But yeah, that's essentially it. Happy to answer any questions.
Thank you very much, BP. So, guys, we have a few minutes left. So, if you want, go ahead and throw any questions you might have into chat, and BP will do his best to answer them. For those of you that joined a little bit late, we are going to post this on YouTube later today, so that will be there. But BP, if we don't have any other questions or any questions, excuse me, coming in, is there anything else you kind of want to touch
Uh-huh.
on for the last maybe 5 minutes or so?
Let me think. I think that's pretty much it. There's a lot of native handling of ETH too. Uniswap, the main difference between V4 and V3 is that there's native ETH handling. There's always potentially some errors there. Um, but yeah, I think the main things to probably watch out. I mean, I just don't want, maybe I'll just stay hands off, but I think the main things to watch out for here is like DOS attacks, out of gas errors. One thing I wouldn't pay too much attention to is like precision errors. Like there's definitely going to be some like one-way precision errors, and we're going to control for that using min amounts. So like I think there's if you don't have an order that's big enough, like especially for certain tokens like USDC, BTC is like a big one. It's eight decimals, and it's a huge dollar. It's 80K, and potentially like if you have a very very small amount, you create scale orders, and you only have like a few cents of BTC, then potentially the precision error could get very, very large. I wouldn't pay too much attention to that. We're going to control a lot of that with the min amount. So we're going to have at least $10 as the min amount order for like BTC, and we could set this for each one. So maybe that's the thing if there's like $10 of BTC as an order and you see something where it's like more than one way off in terms of, the precision, then I think that might be worth bringing up. But yeah, one-way precision's probably not that big of a deal and something we're just gonna uh, assume can happen. But yeah, I think that's pretty much it.
Okay. Well, no problem. No problem. Don't see any questions coming in, so we will wrap it up here. But thank you so much for coming and hanging out with us today, BP. This will help
Of
the
course.
the researchers quite a bit. Just a reminder, guys. Competition 20,000 OP pot goes from yesterday, the 28th of April, to May 5th at 4 p.m. Whatever your local time is. So yeah. Other than that, this will be on YouTube, and we will wrap it up. Thank you everybody for showing up, and have a good afternoon.
Awesome.